Hi, this is a pre-recorded presentation for the 22nd Amsterdam Colloquium. In this presentation, I will talk about two types of high-order readings of Debit questions. In most cases, a Debit question expects an answer that names an entity in extension of the Debit complement, or a GRS quantifier over a set of such entities. For example, in 1, which student came, saying Andy implies that Andy is a student. Saying Andy or Billy implies that both Andy and Billy are students. To capture this question-answer relation, it's usually assumed that the Debit phrase binds a e-type variable inside the question nucleus. It assigns one of the values in its restrictor to this variable, or say the Debit phrase combines with a first-order function, denoted by the scope. For better concreteness, I'm going to present this story using categorical approaches. The framework is chosen just for the convenience of presentation. The core idea of this work is independent from the composition method. In categorical approaches, a Debit question denotes a first-order function, which I call a Q function. This function is only defined for meanings in extension of the Debit complement. And Debit phrases are treated as function domain restrictors. For example, in 2, which student came, which student combines with a first-order function that is defined for any entity and returns a first-order function that is only defined for entities that are atomic students. In this view, the question-answer relation can be easily categorized in terms of function-argument relation. For example, in A, applying the Q function to the entity Andy returns that Andy came defined only if Andy is a student. If the answer names GRS quantifier, and then the question-answer relation will be flip-flopped into an argument function relation. In B, applying GRS quantifier Andy or Billy to the Q function returns that either Andy or Billy came, defined only if both of them are students. In short, in this view, the Q domain is a set of entities. It's a subset of the extension of the Debit complement. In this talk, however, I'm going to argue that, in some cases, a Debit question must be interpreted with a higher-order reading. In this reading, the Q domain of the question is a set of GRS quantifiers. As a roadmap, I'm going to start by presenting evidence for those readings, and then talk about constraints of the Q domain, including positiveness and homogeneity. And then we'll talk about derivation and distribution of the two types of high-order readings, including conjunction-admitting reading and conjunction-rejecting reading. To get started, let me first introduce some basics of coordinations and GRS quantifiers. For coordinations, disjunctions over set denoting expressions are analyzed as unions. Entities are not sets, and therefore they must be Montagu lifted before being disjoined. For example, in 3a, Andy or Billy is interpreted as the union between two Montagovian individuals. Conjunctions are said to be ambiguous between intersections and sums. The intersection reading is analogous to the union reading of disjunctions. For GRS quantifiers, the most important property for this talk is the leave-on property. For GRS quantifier pi and a set of individuals A, we say that pi leaves on A, if and only if for any set B. Pi holds for B if and only if pi holds for the intersection between A and B. We also say that pi ranges over A, if and only if A is the smallest leave-on set of pi. So basically, for any quantificational determiner phrase pi, the smallest leave-on set of pi is the extension of the NP complement. Part A. Evidence for higher-order readings. Assuming that the Q domain of a question is a subset of the extension of the Debit complement, it is two predictions regarding to answers that name a GRS quantifier. First, this GRS quantifier must be interpreted with Y scope relative to any scope expressions within the question nucleus. Second, this answer is not in the Hampton set of the question. Its derivation should involve some extra Boolean operations to the propositions in the Hampton set. And in this session, I will show counterexamples to both predictions, showing that first-order readings is not sufficient. I will also present diagnostics for ruling in higher-order meanings into the Q domain, including diagnostic for disjunction extension quantifiers and diagnostic for conjunctions universal quantifiers. First, a diagnostic based on non-reducibility using disjunctions. Spector observes that elided disjunctions and extension quantifiers can completely address box questions, which are questions with the necessity model. For example, in 6, which books does John have to read, the French novels or the Russian novels? Intuitively, the disjunction can be understood as a complete specification of John's reading obligations. There's no particular book that John has to read, he just has to choose between the French novels and the Russian novels. The similar complete answer rate is also observed with existential quantifiers, which books does John have to read, at least 2 books by Balzac, any 2 books. Spector concludes that questions like 6 admit higher order ratings. In this rating, the question clears involves semantic reconstruction. This rating is paraphrased as in 7. What John's quantifier pi over books is such that John has to read pi. To derive this rating will let the established phrase binds a higher order trace pi across the necessity model. The Q function yielded by this logical form is a higher order function that takes John's quantifiers as arguments. Applying this Q function to a John's quantifier f for r will let this John's quantifier be interpreted at any scope position that pi takes. The box question helps to validate the existence of Boolean disjunctions in the Q domain because its outer space is not closed under disjunction. In other words, the Q function of the box question is not reducible relative to disjunctions. I say that a function theta is reducible relative to John's quantifier pi if and only if combining theta and pi is the same rating as forcing pi to take y scope relative to theta. For example, in 8a, John must read A or B is not equivalent to John must read A or John must read B. In contrast, as in 8b, John must read A and B is equivalent to John must read A and John must read B. So this shows that we're not able to use the semi-diagnostic for Boolean conjunctions. Instead, I'm going to use a diagnostic based on stubborn collectivity to rule in conjunctions. Quantized collective predicates such as formed a team, co-authored 2 papers, are stubbornly collective. For example, imagine that the kids formed the 2 teams in total, A and B formed 1 and C and D formed 1. In this context, it is okay to say the kids formed teams, but bad to say the kids formed a team. Further, 10a is infelicitous because the factive verb know embeds a false sentence. However, the corresponding question embedding sentence is felicitous. John knows which kids formed a team. Intuitively, this sentence means that John knows that A and B formed the team and C and D formed the team. Here arises puzzle. Where does the conjunctive closure come from? Clearly, no matter how we analyze collectivity and distributivity, this conjunctive closure cannot from the predicate or anywhere within the question clears. Otherwise, we should expect 10a to be felicitous as well. So I'm going to propose that the conjunctive closure is applied by the established phrase. A established phrase binds a higher order trace and is Q domain, which includes also Boolean conjunctions. So in 11, the question is paraphrased as for which John's quantifier pi over kids is such that pi formed a team. The Q function is a higher order function. It combines with a Boolean conjunction and returns a conjunctive inference. One might suggest to ascribe the conjunctive closure to some operation outside the question root. For example, Ham's answerhood operator would return the conjunction of all the true propositions in the Hammond set. However, this idea cannot capture the contrast between 13a and b with respect to uniqueness. In the same discourse, it is infelicitous to say John knows which 2 kids formed the team because the sentence implies that among the relevant kids, exactly 2 of them formed one single team. This uniqueness requirement is standard explained by Diak's presupposition, which says that a question is defined only if it has the strongest true answer. For the plural question, which kids form the team, the strongest true answer is the conjunctive answer, which is derived based on Boolean conjunction. While for the numeral modified question, which 2 kids form the team, it does not have this strongest true answer because its Q domain does not include Boolean conjunctions. To sum up, by non-reducibility, I argue to rule in Boolean disjunctions and extension quantifiers. By stubborn collectivity, I argue to rule in Boolean conjunctions and universal quantifiers. And furthermore, the combinations of these 2 diagnostics could also rule in Boolean coordinations of those general quantifiers. And now, one may ask whether we're able to make the following generalization. The Q domain yielded by established phrase consists of all general quantifiers over subsets of established complement, and the Boolean combinations of those general quantifiers. And in the next session, I will argue that this generalization is too strong. Higher order meanings in the Q domain are subject to 2 constraints, positiveness and homogeneity. So the question is there any generous quantifier that cannot be included in the question domain? To show that, I'm going to use a completeness test generalized from Spectre 2008. So the sentence of the form X knows Q implies that X knows the complete true answer for Q. For the proposition P, name the short answer X. If P is true but is not entailed by the complete true answer of Q, then we can conclude that P is not in the Hammond set of the question, and X is not in the Q domain of this question. Keeping this in mind, thinking about the truth conditions of the sentence 15 in the context of 14. Assume that John's reading obligations include that he must read at least 2 novels by Andy, and he must read no book by Billy. In this context, Sue knows which books John must read. That's implied that Sue knows the requirement A. Strikingly, it does not imply that Sue knows the requirement B. Sue could be ignorant as to whether John should read any books by Billy. Moreover, it also does not imply that Sue knows the conjunction of A and B. This contrast suggests that the Q domain of the question, which books John must read, includes the increasing generous quantifier at least 2 novels by Andy, and does not include the decreasing generous quantifier no book by Billy. Moreover, it should also do not include the non-monotonic coordination of these 2 generous quantifiers. So given this contrast, Spectre proposes that the generous quantifiers included in the Q domain must be increasing. In the following, I extend Spectre's diagnostic to a broader range of generous quantifiers. Imagine that John is playing the board game. The ABCD in 16 lists out a set of game rules, and each game rule specifies a generous quantifier that ranges over a set of cards. In particular, in A and B, the red ones are increasing generous quantifiers. In C and D, the blue ones are decreasing generous quantifiers. A Spectre would predict the sentence 17, Sue knows which cards John must play. That's implied that Sue knows about the obligations that would name an increasing generous quantifier. And does not imply Sue knows any of the requirements that would name a decreasing generous quantifier. It also correctly predicts that she doesn't necessarily know the requirements that would name a non-monotonic GQ coordination. So far so good, but now thinking about new requirement. The game requires that John play exactly 2 hearts. In this case, Sue knows which cards John must play. That's implied that Sue knows the requirement that he has to play exactly 2 hearts. So, Spectre's increasing constraint does not capture this condition. More generally, this constraint faces a dilemma. On the one hand, we want to include non-monotonic GQs. On the other hand, we want to exclude non-monotonic GQ coordinations. So, in my view, whether a high-order meaning can be included in the Q domain is determined by its positiveness, not its monotonicity. Saying a GQ is positive means that it ensures the existence relative to its smallest Levant set. For any pi of type EDT, pi is positive means that pi entails the generous quantifier derived by applying sum to the smallest Levant set of pi. The following table compares increasingness and positiveness. You can see that in most cases, these 2 constraints predict the same classification. At least 2 books is positive because it entails some books. At most 2 books is not positive because it does not entail some books. However, these 2 constraints make different predictions for non-monotonic quantifiers such as exact 2 books and 2 to 10 books. Those quantifiers are positive because they entail some books. The previous slide has only considered cases that involve a simplex generous quantifier, but Spectre points out that the positive constraint does not exclude the unwanted non-monotonic GQ coordinations such as some A and no B. This quantifier is positive because it ensures the existence of something that is A or B. Fortunately, we can exclude those complex non-monotonic GQs manually. For any GQ pi, we can decompose it into the conjunction of pi plus and pi minus. Pi plus is the strongest increasing GQ entailed by pi, and pi minus is the strongest decreasing GQ entailed by pi. To exclude the complex non-monotonic GQs, we just exclude the non-monotonic GQs where the conjoined pi plus and pi minus range over different sets. And I call quantifiers that satisfy this condition as being homogeneous. For any pi of type EDT, pi is homogeneous means that pi is monotonic, or the smallest Levant set of pi plus and the smallest set or pi minus are equivalent. By this definition, exact 2b is homogeneous because its pi plus and pi minus both range over the set B, while sum A and no B is not homogeneous because its pi plus ranges over the set A, while its pi minus ranges over the set B. In sum, for the Dawich phrase of the form WHA, the Q domain eared by the Dawich phrase in the high-order rating is the set consisting of the positive homogeneous GQs ranging over a subset of A. I represent this set as HA. Accordingly, for the question which books does John have to read, we can represent its question denotation as in 18. In particular, for the high-order reading, the question denotation is a high-order function that takes arguments of type ETT that are members in the set H books. So far, it's still unclear where the constraints like positiveness and homogeneity come from. They might be in the lexicon of the H shifter, or maybe presuppositions of the high-order Dawich trace, or maybe constraints on semantic reconstruction. Part C. Distributing the conjunction at the median reading. High-order readings seem to be unavailable if the Dawich phrase is singular marked or numeral modified. As in 19 and 20, uniqueness effects show that those questions cannot have answers naming Boolean conjunctions. It is incoherent to say, I know which book John read, book A and book B. It's incoherent to say, I know which two kids form the team, the 2 boys and 2 girls. However, in contrast to numeral modifiers like 2, the PP modifier in a group of 2 does not trigger uniqueness. It is coherent to say, I know which kids in the group of 2 form the team, the 2 boys and the 2 girls. So it seems that the availability of a high-order reading is somehow sensitive to the internal structure of the Dawich phrase. This tree diagram illustrates the internal structure of Dawich phrase. At the very bottom of the tree, the small np is the root that creates a similarity structure, which is a set of entities closed under summation formation. In the projection of the numera, the head is a cardinal predicate that checks cardinality. And next, at the phi head, there could be a number of features that checks atomicity. I propose that the H shifter, which converts a set of entities into a set of genus quantifiers, must be applied locally to the small np, and that is the place where roots are assigned to the category of nouns and are structured into similarities. This analysis easily explained why high-order readings are not available in singular marked questions and numeral modified questions. First, the H shifter cannot be used in singular noun because genus quantifiers are not atomic, while the singular feature asserts atomicity. Second, the H shifter cannot be used in numeral modified noun because numerals must check cardinality and cannot combine with a set of genus quantifiers. In contrast, the PP modifier in a group of 2 does not have this requirement. So, interim summary. For constraints, I argue that high-order meanings in the Q domain must be positive and homogeneous. In the derivation, a H shifter is applied to the small np within the Dawich complement and returns a high-order restrictor. Dawich movement leaves a high-order trace in the question nucleus. For the distribution, I have shown that if Dawich complement is singular marked or numeral modified, the atomicity and the cardinality requirements would block the application of the H shifter, making high-order readings unavailable. The last part, the puzzling disjunction-only reading. Strikingly, in responding to box questions where the Dawich complement is singular marked or numeral modified, narrow scope disjunctions are not as bad as conjunctions. For example, in 24, it is certainly bad to say, I know which book John has to read, book A and book B. But it's not too bad to say, I know which book John has to read, book A or book B. And similar pattern is same with the numeral modified question 25. The narrow scope disjunctions are even more readily available with disjunctive answers. For example, in 26, which textbook should we use for this class? One can perfectly say Hammond-Kretzer or Minian grammar. The choice is up to you. A similar observation is seen with answers to questions with a possibility model, which we call statement questions or mention sum questions. As shown in 27, elite-dimensional answers to those questions can have either a conjunctive form or a disjunctive form. What can I use as a textbook for this class? Hammond-Kretzer or Minian grammar, or say Hemerkreiser, and Minogramma. In particular, disjunctive answer will be understood as free choice. Hirsch and Schwarz observed that a singular marked diamond question admits a multi-choice reading if the uniqueness inference invoked by the singular adapted phrase takes narrow scope. For example, in 28, which letter could be missing FO underscore M? The missing letter could be A, and the missing letter could be R. Here, we're interpreting uniqueness under the scope of the possibility model. In Hirsch and Schwarz's original example, they use a conjunction of two full sentences. However, if expressed in an enlightened form, the machine-all answer to a singular marked diamond question has to be a disjunction. For example, in 30, which letter could be missing in FO underscore M? One can say A or R, but not A and R. So here arise two puzzles. One, why those questions admit and only admit disjunctions? And second, why this reading is available despite that the adapted phrase is singular marked or numeral modified. Next, I show two ways to account for these two puzzles. A uniform approach considers the conjunction-limiting reading and disjunction-only reading the very same reading. It says that, just like entities, disjunctions may satisfy the atomicity requirement or the cardinality requirement. A generous quantifier pi is said to be atomic if it satisfies the two requirements. A. The minimum weighted sets of pi are all singleton sets. B. Every member in the smallest Levant set of pi is atomic. By this definition, for example, if we have three relevant students ABC, and then for the singular noun student, the first order rating is going to be a set of the three atomic elements ABC, and the higher order rating will be the set of Boolean disjunctions of the corresponding multi-covalent individuals. Furthermore, saying a generous quantifier pi has the cardinality n can be defined analogously. So in this approach, the derivation assumed for the conjunction and meaning reading also extends to the disjunction-only reading. By contrast, the second solution assumes a different derivation for the disjunction-only reading. It says that the disjunction-only reading involves syntactically reconstructing the Debye complement to the quantitative clears. So you can see in 31, for both readings in A and B, there's a copy of the book within the quantitative clears. In the following, I will talk about the predictions of this solution. For box questions, conjunctive answers are unacceptable because conjoining two statements of uniqueness yields a contradiction. For example, in 32, which book does John have to read? The higher order reading is read as for which generous quantifier pi. It has to be the case that for pi x, x is the unique book that John read. As in B, applying this Q function to a conjunction yields a contradiction. It's read as it has to be the case that the book that John read is book A and book B. For diamond questions, I have previously argued that the disjunctive mention-all and conjunctive mention-all are derived by different logical forms. In particular, the conjunctive mention-all arises if the higher order adapted trace takes scope above the possibility model, while disjunctive mention-all arises if the higher order trace is associated with an operator that activates free choice. So basically, on the second picture, you can see that applying that operator though to the disjunctive answer, returning a free choice inference, which is semantically equivalent to the conjunction of the two individual answers. So, in prediction, for a singular marked question, conjunction over wide scope uniqueness yields a contradiction. It's incoherent to say A is unique professor who can chair alone, and B is unique professor who can chair alone. But for disjunctive mention-all, free choice over narrow scope uniqueness does not yield a contradiction. It's coherent to say it is possible that A is the unique professor who chairs alone, and it is possible that B is the unique professor who chairs alone. In conclusion, evidence from questions with necessity models or collective predicates show that sometimes a Debye question must be interpreted with higher order reading, and the generous quantifiers that can serve as complete answers of questions are subject to two constraints: positiveness and homogeneity. Higher order readings arises if the edge shifter converts the Debye restrictor into the set of GQs, and if the Debye phrase binds a higher order trace. And therefore, higher order readings are inevitable if the application of edge is blocked, such as by the atomicity or cardinality constraint in singular or numeral modified nouns. And finally, we see a puzzle that singular marked and numeral modified questions admit only disjunctive answers. I provide two solutions to this puzzle. So that is the story. Thank you for your attention.